Hello, my name is Sahana Kumar, and this summer, I worked with the Search Place Planning Laboratory on multi-agent pathfinding, maximizing interagent distance. In recent years, research in multi-agent pathfinding has accelerated rapidly. This is partially due to the variety of applications, all with increasing prevalence in today's world, including autonomous warehouse management, complex video game systems, and aircraft control. It also allows the same number of tasks to be executed with greater speed and accuracy, as agents can be specialized for different tasks. However, multi-agent systems also present a diverse and increased set of challenges when it comes to pathfinding, the primary one being collision avoidance. When several agents move dynamically on a shared field, the chance of potentially catastrophic collisions rises exponentially. To prevent agents from attempting to occupy the same space at the same time, prioritized planning is used. Each agent is assigned a priority, and lower priority agents use higher priority ones as dynamic obstacles. However, it is not merely enough to ensure that agents do not occupy exactly the same space. Each agent requires a buffer distance around it to avoid collisions caused by slight errors in path following and space constraints. This buffer distance is difficult to predict, however, as it depends on several factors, including the speed of each agent, difficulty of the terrain, proximity to other static obstacles, and the extension of any appendages by either agent. As such, it is beneficial to ensure that each agent has a buffer distance that is as large as possible around it to avoid collisions. Here we propose a system where inter-agent proximity is heavily penalized. This may result in longer paths, but it also results in higher distance between agents, which allows faster path traversal and, more importantly, eliminates the possibility of collisions. For testing, we used an environment with a team of n agents on a 2D grid of dots, where each agent can only move up, down, left, or right, and each movement has a cost of 1. To the right, an example of such an environment is shown with a 6x6 grid with 2 agents, their paths shown in orange and blue. Static obstacles are highlighted in red. As shown, the orange agent has higher priority, causing the blue agent to take a longer path to avoid colliding with it at position 3, 3. For any agent AK, where k is between 1 and n, its position at a given time is specified by the coordinate pair x akt, y akt. The cost function shown below attempts to maximize the distance between all agents at each step. This is seen as it iterates through each set of agents and attempts to maximize the distance between them. By maximizing this cost function, we yield an optimal path. In order to implement this cost function, we assign a highly conservative minimum distance, outside of which we assume there is no risk of collision between agents. For the purpose of this example, we assume this minimum distance is set to 5. When the agent comes inside this distance, the distance cost imposed increases exponentially. For example, at a distance of 4 from the other agent, the distance cost is 1. At 3, it is 4. At 2, it is 9, and at 1, it is 16. This makes agents coming between 1 unit of each other virtually impossible, and thus greatly eliminates the chance of collision between agents. This algorithm places high value on interagent distance, allowing faster path traversal and eliminating the possibility of collisions. Future improvements to it may include integrating the base algorithm with conflict-based search, experimenting with linearly increasing distance penalties rather than quadratic, and finding an optimal way to assign this minimal distance value. Thank you for your time. This work was made possible by mentorship from the Search-Based Planning Laboratory, support from the Robotics Institute Summer Scholars Program, and funding from the National Science Foundation.